Students, today we are going to do the chapter Semiconductors, which is the last chapter in your syllabus. So let's begin. So what are semiconductors basically? If you remember, in the periodic table you have studied about certain elements which behave both as conductors as well as insulators. For example, silicon, germanium, etc. These are the semiconductors. And in chapter 3 electricity also you have studied about the energy gap in semiconductors, if you remember. So semiconductors will show conductivity only when the temperature is sufficiently high. At low temperatures they will just behave like other insulators. So let's first study about the special properties of semiconductors. They have a much higher resistivity than metals, of course. That's why they are not able to conduct at low temperatures. They have high and negative temperature coefficient of resistivity, the alpha. You have studied, right, in the third chapter. And they have lower density of charge carriers. That means the number of charge carriers, the number of free electrons and holes are less as compared to metals. This is the reason that for conduction in semiconductors there needs to be a special criteria. Now there are two different types of semiconductors. First of all, let's study about intrinsic semiconductors. The pure semiconductors are called intrinsic semiconductors. They are not doped with any impurities. In intrinsic semiconductors, the number density of electrons is equal to the number density of holes. So intrinsic semiconductor is just the naturally occurring semiconductor. We are not putting any impurity in them. So why impurities are added, we will learn about that later. So the semiconductor which are known as intrinsic semiconductors, they are devoid of any sort of impurity. They are just the tetravalent atoms, like for example silicon or germanium, without any impurity. So they are not enhanced in any manner for increasing their conductivity. Also, in intrinsic semiconductors, the number of free electrons will be equal to the number of holes. So holes is nothing but just a vacancy or an empty space in the energy band. So we'll come to that later. So since we are not adding anything extra, so that's why the number of electrons will be equal to the number of holes. NH, number of holes, will be equal to Ne, that is number of electrons. Now what is doping? I guess you have heard about the term doping in case of athletics or other sport events. So doping is something we inject into our body in order to increase our working, increase our capacity. Similarly, doping is a procedure of adding a desirable impurity. The impurity can be another atom to a semiconductor so as to increase its conductivity. So we are going to enhance its conductivity. In order to do that, we are adding some extra impurity in it. Extrinsic semiconductors. So in intrinsic semiconductors we studied that nothing is added to it, it's just the naturally occurring semiconductor crystal. In case of extrinsic semiconductor, we are adding or doping some impurities into the semiconductor in order to make it much more better. So there are two different types of extrinsic semiconductors, N-type and P-type, very important. So what happens in N-type semiconductors? The semiconductors which are doped with pentavalent impurities, this is the most important thing, pentavalent impurities, that means the atoms which have a valency of 5, those atoms will be added to the semiconductor to increase its efficiency. So what are such examples? Arsenic, antimony, phosphorus. Now talking about P-type semiconductors, semiconductors which are doped with tetravalent impurities, that means which have 4 electrons in the I guess it's a little bit wrong, it should be trivalent impurities. Please make the correction. I will correct the PDF once again. So trivalent impurities, that means the outermost shell consists of 3 valence electrons. So examples of such impurities are boron, aluminium, indium. So in both the cases what we are doing, we are adding some impurity, we are adding some atom in order to increase its efficiency, in order to increase its conductivity. Now if I just understand that what happens when N-type and P-type semiconductors are made. N-type semiconductors are made using pentavalent impurities. So out of the 5 valence electrons, 4 electrons are already bonding with the 4 other electrons present in the semiconductor. Because if you remember, silicon has 4 electrons in its valence shell, and if 5 more electrons are added, like a pentavalent impurity is added, the 4 electrons of that pentavalent atom will go and combine with the other 4 electrons of the semiconductor. So 1 electron is left behind, that electron will contribute to the conductivity. Similarly, in case of P-type semiconductors, we are adding a trivalent impurity. That means out of the 4 electrons of the semiconductor, 3 are getting bonded with the trivalent impurity, right, because they contain 3 electrons in its outermost shell. So one space is left empty, that is known as the hole. So in both the cases, either electron density will be a little more, either the hole density will be a little more. Because of this difference in the electron and hole densities, they will be able to conduct easily. I guess it is clear. Now coming to what are energy bands, we will see the diagram in the later slide itself. So let's first understand about energy bands. An enormously large number of energy levels closely spaced in a very small energy range are known as energy bands. So you have studied about energy levels. Each of the orbit is known as an energy level because it contains a certain amount of energy. So when we are discussing about energy levels in case of semiconductors, we are not considering the revolving nature of the orbits. We are just considering as if they are stationary and they are very closely spaced. So whenever some energy levels are closely spaced with one another, they are known as energy bands. So there are basically 2 types of energy bands. One is the valence band and one is the conduction band. Conduction band will help in conduction, of course, and valence band is the band of the outermost shell. Okay, now let's see what are the differences between metals, insulators and semiconductors on the basis of their energy bands. So in case of metals, the conduction band is partially filled already because of course it is a metal. So conduction will happen either way without temperature, by increasing temperature, either way. So the conduction band is always partially filled. But in case of insulators and semiconductors, the conduction band is empty. That means there are no electrons in the conduction band yet. On increasing the temperature in semiconductors, electrons will jump from the valence band and move to the conduction band. Now, in metals, the valence band is completely filled. Valence band means the valence electrons, the band containing the valence electrons. In insulators and semiconductors, the valence band is completely filled. So in both the cases, the valence band is completely filled, and in metals itself, the conduction band is partially filled. So this means that metals can conduct electricity in any condition, but for insulators will never conduct electricity, of course, but for semiconductors, we need to increase the temperature so that we can see conductivity. Now in case of metal, there is another very important thing. Either there is energy gap between the completely filled valence band and the partially filled conduction band, or the conduction band and the valence band partly overlap. So know that in case of a metal, the conduction is very easy to occur, as a result of which what happens, the conduction band and the valence band have a very slight gap between them, or in most of the cases they are actually overlapping with one another. But in case of insulators, the energy gap is more than 3 electron volts. If you remember, in the 3rd chapter we have done this thing. But in case of semiconductors, the energy gap is less than 3 electron volts. Since the energy gap is less, therefore the electrons from the valence band are able to jump into the conduction band and show conductivity. So this is the process which happens. But in case of insulators, the energy gap is higher, as a result of which the valence electrons cannot jump from the valence band to the conduction band, and hence they do not show any conductivity. I hope it is clear. The highest energy level in the conduction band filled with electrons at absolute zero is called Fermi level, and the corresponding energy is known as Fermi energy. So inside the conduction band, the highermost energy level that is present, which is filled with electrons, and the temperature has to be absolute zero. In that condition, it is known as the Fermi level. That energy level is known as the Fermi level, and the energy which is there in that level is known as Fermi energy. So this is a good question. Question can be asked on the basis of this directly. Now if you see the diagram which I was talking about, in case of metals, see, there is overlap between the conduction band and the valence band over here. But in case of semiconductors, the gap is small, less than 3 electron volts. But in case of insulators, the valence band and the conduction band have a huge gap. So the electrons are not able to make the transition. The electrons are not able to jump from the valence band to the conduction band, since the gap is so huge. As a result of which, we are not able to see any conductivity. Now let's study about the energy band diagrams of intrinsic semiconductors and extrinsic semiconductors. This is a very, very important diagram. Every year at least one question is asked from here. So please mark this as very important. So EV represents the valence band and EC represents the energy of the conduction band, and EG represents the energy gap. So at 0 Kelvin, that means at a normal temperature, we are not increasing the temperature now. What happens? In the valence band, there are electrons. Electrons are represented by the red dots. So electrons are fully filled in the valence band, but see, in the conduction band, there are no electrons, like we have just studied in the difference table. Now, when the temperature is increased beyond 0 Kelvin, some electrons, 4 electrons, have jumped to the conduction band, and in place of those electrons we are seeing some holes. The blue color dots are the holes, that means empty spaces. So as we increase the temperature, some electrons are jumping into the conduction band and hence showing conductivity. Now talking about extrinsic semiconductors, N-type and P-type semiconductors. We know in N-type semiconductors, the number density of electrons will be more because we doped it with the pentavalent impurities. So see, the number density of free electrons are more in the conduction band. But in case of P-type semiconductors, the number density of holes will be more in the conduction band. So as you can see, there are just 2 electrons and the rest of it will definitely be holes. So in this manner, we can make the band energy diagram for extrinsic semiconductors. This is a very important part of the chapter. So go through the diagrams properly. Even you will have the same diagrams in your book. So these diagrams are extremely important. Go through them properly and practice them, because lots of questions can be asked on the basis of this particular topic. Now let's differentiate between extrinsic and intrinsic semiconductors. First of all, in intrinsic semiconductors, they are not doped with any impurities. They are just purely the semiconductor crystals that we observe in nature. But in extrinsic semiconductors, they are doped with some impurity. In intrinsic semiconductors, the electrical conductivity is low naturally because they are not doped with anything. So the electrical conductivity will be low. But in extrinsic semiconductors, the electrical conductivity is quite high. The number of electrons is equal to the number of holes. I told you at the beginning itself that in intrinsic semiconductors, the number density of free electrons will be equal to the number density of holes. But in extrinsic semiconductors, in N-type, the electron density will be more, like we just saw in the diagram. And in case of in case of P-type semiconductors, the number of holes will be more. So if a semiconductor crystal is given to you and you're seeing that the number of holes is more as compared to the number of electrons, that means it is a P-type semiconductor, and vice versa. In case of intrinsic semiconductors, electrical conductivity depends upon temperature. Of course, we have studied that on increasing the temperature only, a semiconductor will behave like a conductor. So temperature is very much important for semiconductor. But in extrinsic semiconductors, not only temperature is the essential factor, along with that how much doping we are doing, the dopant concentration, how much doping we have done to the semiconductor crystal, that is also playing a major role in determining the conductivity. Now let's see the differences between N-type and P-type semiconductors. I guess almost all of it is known to you. Let's just do a quick recapitulation of it. N-type semiconductors are prepared by doping with pentavalent impurities, and P-type semiconductors are prepared by doping with tetravalent impurities. The first point is the type of doping that we have done. The impurity atoms provide free electrons and are called donors. I told you in N-type semiconductors, 1 electron will be left extra by each of the pentavalent atoms. So they are also called donors. They are giving electrons. And in case of P-type semiconductors, since they are creating some vacancy, they are known as acceptors. Okay. The electrons are the majority charge carriers and the holes are the minority charge carriers. Naturally, electrons are more in number, so they are called the majority charge carriers, and holes are called the minority charge carriers. In P-type semiconductors, it is just the opposite. Since the number of holes are more, so the holes are the majority charge carriers, but the electrons are the minority charge carriers. The free electron density is much greater than hole density. Already told you about it. Similarly, in P-type semiconductor, the hole density will be more than the electron density, right? Now, like I said you at the beginning, what is a hole? Hole is nothing but just a vacancy. We are just calling it hole to denote an empty space. The vacancy or absence of any electron in the bond of a covalently bonded crystal is called a hole. Now, for an intrinsic semiconductor, Ne, that is number of electrons, is equal to NH, number of holes, is equal to Ni. We denote it using Ni. So let us do the first question on the basis of the formula that we just learned. A semiconductor has equal electron and hole concentration of 6 into 10 to the power 8 per meter cube. Okay, so what has been given in the question? Ni has been given. On doping with a certain impurity, electron concentration increases to 9 into 10 to the power 12 per meter cube. So this is the new electron concentration. We know the formula, Ne is equal to Nh is equal to Ni. So if I multiply Ne and Nh, it will be equal to Ni square. Okay. So from here I can find out NH, just simple algebra, right? So NH comes up to 4 into 10 to the power 4 meter per meter cube. So your question, the first question was identify the new semiconductor obtained after doping. So we see that the electron concentration is increasing. That means it is an N-type semiconductor. And what is the third question? How does the energy gap vary on doping? Always energy gap will decrease on doping. Since energy gap is decreasing, conduction will be better. Okay, energy gap is less, that means electrons can jump very easily to the conduction band and they can conduct. So whenever there is doping either by pentavalent or trivalent impurities, there will always be decrease in the energy gap. Okay, so energy gap decreases on doping. Next, there is a very similar question now. A semiconductor has equal electron and hole concentration of 2 into 10 to the power 8 per meter cube. So Ni is given as 2 into 10 to the power 8 meter per meter cube, 2 into 10 to the power 8. And on doping with a certain impurity, the hole concentration increases. So the hole concentration is now becoming 4 into 10 to the power 10 per meter cube. So again, using the same formula, we can find out the new electron density or the new electron concentration of the semiconductor. So what type of a semiconductor is this? Since the hole concentration is increasing, it will be a p-type semiconductor. And what will happen to the energy gap? Again, since we are doping, the energy gap will decrease. Okay. Next, coming to the most important part of the chapter, that is PN junction diode. This is the junction diode which is used extensively for making different types of apparatuses, and it is one of the most important semiconducting components used in electrical circuits, used in experiments and many other places. So let's see what is a PN junction diode. It is a single crystal of germanium or silicon doped in such a way that one half of it acts like a p-type semiconductor and the other half as an n-type semiconductor. So if you notice the diagram carefully, so one side of it will behave like a p-type region and the other half will behave like an n-type region. So doping is done with trivalent as well as pentavalent impurities, but halfway through. So the p-type region is connected to the anode, or it will behave like the positive end, and the n-type region will behave like the negative end. Okay, very important. So this is the circuit diagram, or this is a symbol rather of a PN junction diode. You have to make a triangle which is representing the p side, and then a straight vertical line which is representing the n side. The n side will be connected to the negative end of the battery, or it will behave like the cathode, and the anode will be the p-type region. So there are two important processes which occur in a PN junction diode. These are the most important parts of a PN junction diode. So let's see. The first is called diffusion, the next one is called drift. So you know about diffusion a little bit from biology, right? So diffusion is the movement of substances from higher concentration to lower concentration. Okay, so the same thing we are going to learn here. So let's see. When a PN junction diode is formed, the P side of the junction has higher concentration of holes, while the N side has a higher concentration of electrons. Of course, P side means there will be more number of holes, N side means there will be more number of electrons. Due to concentration gradient, holes begin to diffuse from the P side towards the N side, and electrons begin to diffuse from the N side towards the P side. So what is concentration gradient? There is a difference in concentration of electrons and holes in both the regions. So because of this difference, the electrons are moving from the N side to the P side, holes are moving from the P side towards the N side. As holes diffuse from P side to N side, they leave behind negative acceptor ions which set up a layer of negative charges on the P side of the junction. Similarly, as the electrons diffuse from the N to the P side, they leave behind positive donor ions which set up a layer of positive charge on the N side of the junction. This sets up an electric field near the junction from N to P side. So when electrons are moving away, that means positive particles are left behind, and when holes are moving away, negative particles are left behind. Because of this movement, because of this motion of the charge carriers from one side to another, an electric field is getting generated. The electric field is from N to P side. The electric field begins from N side towards the P side. Okay, this is an important thing. Consequently, no charge carriers are left in a small region near the junction as shown in the figure. So if you see this figure properly, so the electrons will move from the n side towards the p side. So the red color dots are the electrons, they will move in this direction, and the holes, which are represented by the hollow circles, they will move from the p towards the n side. Because of this movement, what happens, we are going to get a potential or an electric field. So in this region, we can get the electric field. So see over here, a battery is been shown. So this battery does not exist in real life. This is just a fictitious case. That means an electric field is set up. Okay, now in this particular region, if you observe, in this thin particular region, there are no charge carriers, no, there are no holes, there are no electrons. So this region is completely rid of any sort of charge carriers. Depletion region is the small region in the vicinity of the junction depleted of free charge carriers. The one which I showed you, there are no charge carriers in that small region, and it only contains the immobile ions. That means the ions which cannot move, the atoms. Okay, the atoms, after the electrons and the holes have moved away, the atoms which are present, they are found in this thin region. So since there is no electrons or no holes, it is also known as depletion region. I guess you know the meaning of depletion. Depletion means lack of something, isn't it? So in this region, there are no electrons or holes, there are no charge carriers. The next topic is barrier potential. Let's see what it is. The accumulation of negative charge in the P region and the positive charge in the N region sets up a potential difference and acts as a barrier. This is known as barrier potential. There are slight mistakes in the PDF. Please make it okay. The negative charge is getting accumulated in the P region. We learned, right? The electrons will move from the N region towards the P region, and when the positive charges are moving towards the N region, because of this, what happens? A potential difference is created. So in the previous case, an electric field was set up. Now a potential difference is being created. Of course, electrons and holes are moving, positive and negative charges are moving apart, so there is a potential difference created. This potential difference will act as a barrier. It will not allow further movement. It is known as barrier potential, the potential which acts as a barrier. Now, like I said, there are two types of processes. One is diffusion and the other is drift. So on the basis of that process also, there are two types of currents which are developed in a PN junction. Let's see. The diffusion of majority charge carriers across the junction gives rise to electric current from the P to the N side. This is known as diffusion current. So the charge carriers are moving, right, from one direction to another. From P side, it is moving towards the N side, the holes are moving, and from N side to P side, the electrons are moving. Because of this movement, there is an electric current. You know this thing very well, that whenever electrons will move, electric current will be set up. You have studied about this in third chapter. So the current rises from the P to the N side. Naturally, electrons are moving from N to P side, so the current will always be in the opposite direction of the electrons. So electrons are moving from N to P, so current is generating from P to N. This is known as diffusion current. Now, what is drift current? Of course, if current is moving from one side to another, hypothetically there has to be another current which is moving in the opposite direction. So the current set up by the barrier field in the opposite direction, the barrier field, that is the barrier potential. Now in which direction? From N to P side in this case. This is known as the drift current. Okay, so these are the diffusion and the drift currents. Make sure you are going through these particular terms properly, because they can be directly asked or they can also be in the form of MCQs. So this barrier potential that we have just studied about, it depends upon three factors: the nature of the semiconductor, what type of material we are using, the temperature, the amount of doping, how much impurity we have added to it. When doping concentration is more, the depletion region will be small and hence conductivity increases. Very, very, very important. So when we are doping with more number of atoms, more number of pentavalent or trivalent atoms, then what will happen? The depletion region will be small. Depletion region is the region where no charge carriers exist. So if the depletion region is very thin, that means most of the area in the PN junction will be full of charge carriers, and hence conductivity will definitely be more. So imagine there is a question, a diagram has been given. So in one of the PN junction diodes, the depletion region is small, and in the other one, the depletion region is a little bit large. So the one in which the depletion region is tiny, that will be having a greater conductivity. Okay. Now let's see the working of a PN junction. So there are two processes, or there are two ways in which we can use a PN junction. One is in the forward bias condition, one is in the reverse biased condition. So let's see. In forward bias condition, the positive terminal is connected to the P side and the negative terminal is connected to the N side. So if you observe this diagram properly, the P side, this side, is connected to the positive side of the battery and the N side is connected to the negative side of the battery. Also, we are using a milliammeter in this case because the current generated will be having units of milliampere. Now if I talk about the reverse biased condition, the positive terminal is connected to the N side and the negative terminal is connected to the P side. Now observe it. So now in this case, the P side is connected to the negative terminal and the N side is connected to the positive terminal. So just the opposite condition. Also in this case, we use a micrometer or a ammeter which can measure current up to microampere, because in the reverse bias condition the current generated is very less. Let's see, says effective barrier potential, the barrier potential that we have just studied about. So the barrier potential decreases in case of forward bias, but in case of reverse bias the barrier potential is more. Very important. The majority charge carriers begin to flow towards the junction, and in case of reverse bias the majority charge carriers begins to flow away from the junction. That means it is representing the movement of electrons and holes. In case of forward bias they will be moving towards the junction, towards the PN junction, but in case of reverse bias they will be moving away from the PN junction. The width of the depletion region decreases. I told you whenever there will be a thin depletion region, conductivity will be more. So in case of forward bias the conductivity is more compared to reverse bias. But in case of reverse bias, what happens? The width of the depletion region increases. The depletion region will be thicker. As it is thicker, the conductivity will be less. This is the reason that I told you in forward bias we will get the current in terms of milliampere, but in case of reverse bias the current will be in terms of microampere. That means in reverse bias the current generated will be extremely less. Okay. The effective resistance decreases. So in forward bias the resistance is less. Resistance is less means more current. So the same thing we are repeating again and again in terms of different factors. And in reverse bias the effective resistance will increase. Resistance is more, so current will be automatically less. So these are the differences. Make sure you are going through the diagram. Okay. Even if you don't want to make the rheostat, it's totally fine. Make sure you're making the milliammeter and the micrometer. Okay. Along with that, make sure the PN junction is connected to the respective terminals of the battery according to what we have just studied. Now this is the graph. I guess you remember this graph. You have studied it in chapter number 3. So the first quadrant represents the forward bias condition and the third quadrant represents the reverse bias condition. So if you see in the positive y-axis it is written milliampere because it is the forward bias current, and in the negative side of the y-axis it is written microampere. That means it is having in reverse bias the current is very less. Now if you see the diagram properly, you will see that in case of the forward bias, initially the voltage is increasing and the current is also increasing, and it is following a curve like this. Right? For silicon it can be different, for germanium it is different naturally. But when I come to reverse biased, the current is not increasing much. Right? The current is increasing very slowly. The voltage is increasing, but the increment of current is comparatively less. Suddenly, after a certain voltage has been reached, the current will increase rapidly, almost in a straight path. That means it is increasing at an extremely high rate. So there are certain terms which are associated with this. First of all, let's talk about reverse saturation current. When the diode is reverse biased, the reverse biased voltage produces a very small current like we have just seen. This small current is known as the reverse saturation current. Okay, the current which is found in the reverse bias condition, which is increasing at a very low rate, that is known as the reverse saturation current. Saturation means something which is not increasing, something which is saturated, something which is constant. Now, when the reverse voltage across the PN junction reaches a sufficiently high value, the current suddenly increases to a large value, which I showed you here. Suddenly the current will show a peak rise. The voltage at which this occurs is known as the breakdown voltage or the peak inverse voltage. So this point where suddenly the current will increase a lot, okay, with that voltage, when a certain voltage is reached, the current increases a lot. This is known as breakdown or breakdown voltage, or we can also say that it is known as the peak inverse voltage. Now what is the cut-in voltage? Let's see. the voltage at which the forward bias current will increase rapidly with voltage. Okay, it is not increasing like in the breakdown condition, of course, but it starts to increase rapidly, or it starts to increase exponentially. That voltage is known as the cut in voltage. So there are certain terms, so question can be asked on the basis of these terms. Maybe they'll ask you to draw the diagram and mention these points and also define these points. So please go through this nicely. Now this is the last topic in our chapter, junction diode as a rectifier. Now what is a rectifier? Rectifier is a device which can be used for converting alternating current into direct current. AC current we are converting into DC current. So that is a rectifier. Rectifier uses a diode or two diodes. So PN junction diode can be used as a rectifier. Let's see how it works. When a PN junction diode is forward biased, it offers less resistance and current flows through it. We have just seen. But when it is reverse biased, it offers high resistance and almost no current flows through it. So in the forward bias, the current will be quite sufficient, but in the reverse bias, the current is almost close to negligible, right? So because of this, what do we see? In the forward bias, the semiconductor will conduct. In the reverse bias, the PN junction diode will not conduct, and this will go on. That means there is a unidirectional property. That means in one direction, in the forward bias it is conducting, and in the reverse bias it is not conducting. So this unidirectional property of a diode will help us to use it as a rectifier, because we either need the upper peaks or the lower peaks, because we are converting an alternating current into direct current. So in this manner, since in the forward bias it will conduct and in the reverse bias it will not conduct because of what we saw in the graph just now, this procedure can be used to convert or to use a diode as a rectifier. Okay, so a PN junction diode can be used as a half wave rectifier also, or as a full wave rectifier. Now let's see. So in a half wave rectifier, only a single diode is used. This part is the transformer part, and over here we will put the AC input, the alternating current input, and outside we are going to get, on the other side we are going to get the output. So initially the input is an AC current, like you can see it is forming a waveform like so. Output, what happens? The lower part or the lower peak is getting totally cancelled out. Yes, why? Because in the lower peak there is reverse bias, and in reverse bias there is no conductivity. Okay, so how will you write this? How will you explain this? So first of all, you will make the diagram and the graph, and you will write that in case of a half wave rectifier, a single diode is used. During the positive half cycle, the diode will conduct, and hence in the output the upper peaks will be shown. But in the reverse bias condition, since the diode does not conduct, therefore the output voltage in the reverse bias will be negligible, and hence we don't see in the graph. This process continues, and hence you are going to get a half waveform only in the positive cycle. So this is how a diode, a PN junction diode, can be used as a half wave rectifier. I guess it is clear. Now similarly, how it will behave like a full wave rectifier. So we are converting the full wave into AC. That means we need two diodes in this case. So as you can see, there is diode 1 and diode 2, D1 and D2. The input of diode 1 is in this manner, and the input of diode 2 is in the opposite manner. So when one of them is forward biased, the other will be reverse biased, and when the other one is reverse biased, the former one will be forward biased. So in this manner, only the positive peaks are shown. See, I guess it is clear. No negative peaks are shown, only the positive peaks are shown. So this is a full wave rectifier. That means we are converting the AC voltage into a full wave, but in the DC way. Okay, see, there are no lower peaks. So this is the thing. So over here also you will explain that there are two diodes in this case. When the first diode is forward biased, it will conduct, and in that condition the second diode will be reverse biased and it will not conduct, and vice versa. So because of the working of the two diodes simultaneously, we are going to get a full wave in the final output, but in a DC format. I guess this topic is clear. You don't have to explain much. Maximum, the most of the marks for this question is for the diagram and the graph. Okay, so go through it properly. Now let's see two numericals based on PN junction. In this question, there is a table in which the forward biasing and the reverse biasing values of voltage and current have been provided to you. You just simply have to find out the resistance in the forward bias and in the reverse bias. Since in both the forward and the reverse bias, it is not a straight line, rather it is a curve. So we are going to find out the voltage and the current in terms of differences. We have done this in maths, and we do this only when the graph is not linear, the graph has a curve. Okay, so what are the two voltages for forward bias? 2.0 and 2.4. So del V, we will find out del V, or the difference in the voltages, that is 2.4 minus 2, that is 0.4 volts, and the current is 80 milliampere and 60 milliampere, so the difference will be 20 milliampere. Make sure you're converting the milliampere into ampere so that you are able to get the correct answer. So now you know resistance is equal to V by I over here, since you are taking the difference. So del V by del I. So the final answer will come up to 20 ohm. Now in reverse biasing, what happens, the value of the voltage and the current will always be in the negative side, so that's why negative sign has been taken. Okay, don't get confused that from where negative sign is coming. So again we are finding out the difference in the voltage and the difference in the current. Over here the current is in microampere, so again make sure you're converting it into the SI unit, and again now finding out the resistance using Ohm's law. You're getting the resistance as 8 into 10 to the power 6 ohm. So as you can see, it is quite a very high value. Like I said, you in reverse bias the value of resistance is too high, as a result of which conductivity is low. So we have proved it also, and this is how you can solve. Now let's see another numerical. The VI characteristic of a silicon diode is shown in the figure. As you can see, you have to calculate the resistance of the diode at 15 milliampere and also at minus 10 volts. That means you need to consider the forward bias in the first condition and the reverse bias in the second condition. So there's one thing missing in this diagram. So this thing is 0.8, okay, and this one will be 0.7. Now let's see. So at 15, we can see that there is no value given in the graph, right? The values are given for 20 milliampere and 10 milliampere. So we are going to consider it. So let's first of all find out del I. Del I, difference in the current. So what are the currents which are more and less than 15 given in the diagram? 20 and 10. So 20 minus 10, that is 10 milliampere. And what will be del V? As you can see, at 20 it is 0.8. and at 10 it is 0.7, so 0.1 volts. So using Ohm's law, we know R is equal to del V by del I. We have just seen in the previous numerical. So if you solve this, make sure you're converting this milli into ampere. You're going to get the answer as 10 ohm. 10 ohm is the final answer. Now what will be the resistance at V is equal to minus 10 volts? Let us find out. So I'm writing it here at the top, please consider it. So V is equal to minus 10 volts, and what is the current? You can see in this case the current is 1 microampere. So again R will be equal to 10 by 1 microampere. We are going to get the answer as 10 to the power 7 ohm. So again, in the reverse condition, the resistance is so high, 10 to the power 7. But in case of forward bias, the resistance is only 10 ohm. So you can see the difference right through these numericals. So I hope the chapter is clear. If there are any sort of doubt or any question, please ask me in our WhatsApp group itself, and study nicely. Okay.